If you don't know me, I'm Scott with AutomotiveDiag.com. And today I'm going to be talking about dynamic fuel system pressure and flow testing on 2017 and newer GM vehicles that use the J2716 Cent single edge nibble transmission serial data rail pressure sensor. If you've been following along, you know that my previous work has been with analog sensors and on pretty much any other vehicle that uses GDI, being able to do dynamic fuel system testing with my ADDI filter amplifier. The scent decoder is an addition that I've made to the final version that will make doing the same testing on later GM vehicles also possible. If you have much experience with the GDI vehicles, I'm sure you've run into issues where the built-in scan tool tests do not necessarily tell the whole story, and you can still have an issue, but yet they'll still pass the built-in test, which makes our dynamic fuel system testing that we're doing all the more useful. So I'm going to get right into our information here, and I'm going to show you the connections of our test. So here you can see that we have our rail pressure sensor signal, and it's connected to our bypass, which is on green, and you'll actually see the live data coming from the sensor. The black wire here goes straight to our ADDI unit and the J2716 Cent decoder. Our reference low is connected to black. Our red is on our injector control that you'll be able to see here after a bit. And our blue is going to be our high pressure fuel pump spill solenoid current. And this will help us visualize our rail recharges. I'm going to go into the data here, and we are, let's see. Here's our J2716 Cent signal, and you can read up on how this works online, but basically the serial data is transmitted by the time difference between the falling edges. And the J2716 Cent decoder that I created measures these time between these falling edges and calculates the actual binary output. This is actually a 24-bit binary signal. It's two 12-bit channels that are averaged, and the final averaged output goes out as an analog signal that can be used for dynamic fuel system testing. And this binary number that it puts out is equivalent to what your PCM would be getting and you'd be able to see on your scan tool. Now, I'm going to go ahead and go to a different shot here. And this kind of gives you an idea. I like to, whenever I do scope operations, sometimes you can see more when you zoom out. So in this case is no different. Zooming out is often helpful in identifying outlying signals that are abnormal. In this case, you can see we have a very even pattern, and this zooming out works well on many different tests. It works well in any kind of a motor test. If you have a bad blower motor or fuel pump, a lot of times if you see a perfect pattern or a very even pattern when you zoom out, you're probably looking at a good part. Typically, if there's a bad spot in the commutator or something, you'll see something that looks pretty anomalous when you zoom out. So when we zoom back in, oops, went too far. You can actually see, here's our injector 1's control hit that's on the red, as I mentioned in the connections. Here's our flow curve for injector 1. There's where the injector opens. Here's where the injector snaps shut and the pressure rebounds. Not only does the pressure rebound, you can actually see the spill solenoid current is coming in here. And if you understand how this works, the spill solenoid is connected in line between the fuel feed to the high pressure pump from the low pressure side and the high pressure pump piston. And what happens is when the spill solenoid receives current, it closes and does not allow the fuel to pulsate back into the feed line. As long as the spill solenoid's open, then the fuel can be pushed back in against the fuel pump into the feed line and is not forced through the check valve that goes out to the high pressure common rail. But when the spill solenoid closes, the fuel pressure is then, or the fuel is then forced through the high pressure check valve into the common rail, pressurizing the rail. So you can see here, here's our current flow starting on our spill solenoid to close it, and then our pressure increases to the point or the apex of the cam lobe, and then of course our pressure starts to decline when the cam lobe backs away. So we can easily see here that we have a very even build on our fuel pressure every time our spill solenoid activates, which would be indicative of a normal fuel system. We can also see that we have very consistent flow curves of each injector. So here we have 1, 3, 4, 2, back to 1, okay? So this is what a normal signal would look like. Let's see what a bad signal might look like. Once again, we're going to zoom out here so we can see what our pattern actually looks like zoomed out. And as I mentioned with the other pattern, you can see it looks pretty unstable and pretty uneven. Whenever I do any kind of scope operations, I will tend to zoom out first and start zoomed out like this, and then I'll go in and I'll try to find the weirdest looking part I can find, which is right in this area. And I'm going to go in and we're going to analyze this. So we can still see easily here that we have a normal flow drop or a normal flow curve for cylinder 1 when the injector comes in. There's our activation, there's our flow curve, there's a rebound, there's our spill. Okay, so we've got 1, 3, 4, 2, back to 1, same as the previous example. But something else that's interesting to note here is bear in mind that your PCM is always attempting to maintain a set point on your high pressure common rail output pressure. And in most cases, it's going to be between about 5 and 600 PSI. That's somewhere between 2 and 3 megapascals. Whenever that shifts off of its set point, you're going to see a change in the spills on time. And in this case, you can actually see it because no fuel injector event happened here. This is 1, here's 3, and there's literally no flow curve. That can clearly be seen. And because of that, the overall pressure is higher. So you can see the next spill event, duty cycle, is much shorter. And it's trying to bring the pressure down because the average pressure is too high. And then you'll see that the pressure comes down, the next pulse, it's not near as high, and then you can see that it starts to bring the duty cycle back in to try to stabilize it. And of course, anything in scope operations, we always want to make sure that we look at the first destabilization on the left, because everything after the primary destabilization point, which is here, is going to be somewhat skewed. Notice we've got variations in our flow drop levels here. And the primary reason we have these differences in the flow drop levels is because our rail pressure is actually different between these 2 points. So obviously we're going to have our pressure dropping to a different point. Notice though our flow curves are still very consistent, and we have about the same angle of our flow curve on each drop. So this has been really a journey that I've gone through, and I really appreciate everybody that's been with me through this. I'd like to thank everyone for following along, and I'm making tremendous progress toward the final version. The final version of the ADDI is going to be fully digital controlled, and in fact I have a prototype that is fully digitally controlled. Might do a video on that after a bit, but it will also incorporate the scent decoder, the filter amplifier that started the project off. Not only that, it will also have a third operating mode that will be a frequency mode. And this frequency mode will allow us to do a misfire test based upon the mass airflow sensor or the crank sensor, very similar to what can be done with the math channels on a picoscope. The difference is it will be able to be done on any scope with plug and play with no math channels. But then you can actually see individual misfires as cylinders decelerate and accelerate. Pretty excited about that. It's gonna be good. There's a lot of other features and uses of the ADDI that I haven't even talked about yet that I've found in using it. So once again, folks, thank you for following along with me. If you want to get in touch, you can reach me at www.AutomotiveDiag.com, or you can reach me on Instagram.